quarks and the original strand model quarks, because you see, if it were to have any vacuum expectation value, then it will produce a mixing between the new quarks and the strand model.
Sorry, X is the lightest new particle?
With baryon number.
So it doesn't couple to strand model fermions?
It does not. It will not decay into any other strand model fermion, because
what prevents it?
The conservation of baryon number and the charge, because in the standard model we have
if you here you decide that X is a dark matter candidate, and there is the term for interactions before the slide. That means why it is not fixed.
Sorry?
Why it is not fixed, these particles, if there is interactions?
I didn't get your question. What is not fixed?
That means you decided that X particle is the dark matter candidate, yeah?
Maybe.
And here there is, you write the Lagrangian for interactions. That means that this particle can interact with the...
strand models.
Yeah. That means it is possible to fix, to measure these particles. Up
yes,
to now,
yes, that is.
It is not measured.
And it is experimentally measurable. See, if this model is correct, then it will be detected in the LHC in coming years. And if it is wrong, then it will not be detected. So,
the quarks being fractionally charged, if I were to put some quarks with this to form a baryon family, there'd be three things to put together to form a baryon, right? Including X would be a candidate for that as a quark.
Right.
Then I would have fractionally charged particles available, which would not be quarks. There'd be free particles with fractional charge.
Yeah.
Where did they go?
I'll have to look at it. I didn't get your...
Well, I could take something that has baryon number 1/3, baryon number 1/3, and put it with this baryon number -2/3.
Right.
The baryon number 1/3 and the baryon number 1/3 would have fractional charges as well.
Yes, absolutely.
Both put together will have a fractional charge.
Yes.
Because there are only two. This has zero charge.
Yes.
So this new particle, XDD, if I got it right, will be a fractionally charged
Some
meson-like thing,
Yes.
baryon meson, a fermion with zero baryon number.
Yes, I'll have to look
And
at it.
now I ask, why don't we see these?
Well, I don't know, because X is a scalar particle. It's a scalar field. So I don't know how it will combine with or make a
It's a
bound
scalar
particle.
field with baryon number -2/3.
Yes, it has that.
I can still fit this scalar field with two baryon number 1/3 particles.
Yes.
Right?
Right.
So I'll get a meson which is whatever, which is fractionally charged.
Also scalar.
But that will not be a gauge invariant term, will it?
No,
Because
yeah.
those Qs don't carry 1/3 charge. The new Qs.
Yeah, how many Qs you have added?
Qs carry 1/3
They
charge.
carry
They're just
1/3.
There are
additional.
standard models.
And now I've got a fractionally charged particle I've constructed,
Well,
which should be there in my dark matter.
well, I am considering a modification of this model also, in which, because if we make that modification, X will lose its baryon number. Then X will be a particle without any baryon number. But
Yeah, but then it
you are-
won't do what you wanted it to do first.
the decay
You
is
needed the baryon number.
no. Well, because in that case, the new quarks will carry just the same baryon number as the standard model quarks, 1/3 baryon number. So in that case, we won't need X to have any baryon number.
I'll talk about it when I see that one. I
Yes,
haven't seen that at all.
I-
So this one I have a problem with.
Yes. Well, I'll think about it, because I'm still working on it.
Yeah, this one
It's
is.
new consideration. Okay. Okay, and similarly, we need the new electrons to decay, as we needed new quarks to decay. So, in this case, we assume a new scalar field SL, and we also assume that this SL does not have any vacuum expectation value to avoid any phase variation in the electron sector. But SL is not dark matter candidate because it can decay into other fermions. Now, the total Higgs sector needed in this model comprises of the standard model Higgs boson and four other particles. That two we have already seen, X and SL, and we also need these two, SB and SL prime. These two Higgs bosons will break the gauge symmetry, UB1 and UL1 symmetries, and they will generate masses for the gauge bosons that couple to the baryon and the lepton numbers. But the masses for other normal fermions are generated by the standard model Higgs boson in the usual way that we do in the standard model. So the complete Higgs potential is this. It has the form, the field phi. Basically, I've written it as phi star, but it's actually phi dagger. So, okay. So these are the main features of this model. You see, what are the good things that this model tries to explain? The first is that it attempts to explain one of the problems with the standard model, that why baryon number is conserved and lepton number is conserved, because they do not appear in the mathematical framework of the standard model. This model nicely fits them into the standard model's mathematical framework, and we supposedly also get a dark matter candidate. And one point that I have not discussed because I'm working on it is that using a modest fine tuning of some parameters, we can generate the baryon excess in the universe using this model. So these are the three good things that this model proposes, and this model may have the potential to solve these questions. And there are some bad things also. The biggest bad thing is that it asks us to add new generations of particles with very strange baryon and lepton numbers. Baryon numbers 1, 3 times as large, and lepton numbers again 3, which is again 3 times as large. So I am thinking on making some changes into this model by adding not one new generation of fermions, but adding 3 more generations of fermions with the usual baryon and lepton numbers. So in that case, we would not need, first of all, X will not then carry any baryon number, because we're going from a particle with baryon number 1 by 3 to another particle with baryon number 1 by 3, and on the way we are emitting an X particle. And because baryon number is a conserved quantity in this case, so X should not have any baryon number, because moving from a particle with baryon number 1 by 3 to another particle of baryon number 1 by 3, and in the way it is being emitted, so X will not carry any baryon number. And because it will not carry any baryon number, so I hope that it will not couple to this the baryon number gauge boson. And one of the decay channels, one of the annihilation channels for the X particle that Mark Weiss has considered in his paper, this channel will be eliminated because X will no longer couple to this ZB boson. And the only annihilation channel possible for X will be through the standard model Higgs boson that has already been studied in literature many times. So these are some of the modifications that I think are possible with this model. Now, concluding my presentation, I think this model can be a step in the right direction, because baryon number symmetry and lepton number symmetries are empirical symmetries that we have seen are very resilient from experimental data. So it will be logical to include them into the mathematical framework of the standard model. Similarly, because it gives us a good dark matter candidate, hopefully a good dark matter candidate. And if WIMPs are not found at the LHC, and this model is indeed verified, then this will be a very good alternative to WIMPs. And also, modifications that I have proposed can open up new avenues for research in the future towards a better understanding of where unification research will be going on. So,